Okay, we're live. Mateusz.
All right. Hello and welcome everyone to the sixth episode of Flashwares. This time it's Lit. Lit protocol is a centralized network that utilizes cutting-edge cryptography, sealed confidential hardware, and peer-to-peer networking to securely generate and manage non-custodial keys and execute private and immutable programs. That's what you'll get if you go look at the docs of Lit protocol. And here we have Harry, who is a software engineer at Lit, who will be getting us through the high-level design and then into some Q&A. All right, Harry, take it away.
Hey, thanks so much. I'm here to speak about how we use TEs at Lit. I know it might be a bit different to how the Mev guys normally use it, so we'll go through that. As I was introduced, I'm a software engineer over at Lit, and I focus mainly on sort of the ops side and deploying our node across multiple different machines. Before we start on the TE side, I think it's good to give people a primer on Lit in case they haven't seen or used it before. So our main feature is these decentralized programmable keys. Instead of your key just being a public-private key pair that you hold on to yourself, it's sort of a key with a set of rules attached to it. Maybe you want to have a key that can be claimed. So if I wanted to send you funds, but you don't have a key yet, I could say this key can be used by anybody who can prove that this is their email or sort of that flow, which we can go into a bit more as we get through. Just to highlight a few of the people that are using Lit already, we work with Fox Corporation, Gitcoin, Lens. Fox are using it for some of their new verifiable stuff there. So I think it's quite interesting the adoption that's already been done. And we have blog posts about the work we've done with other big players as well. But before I go on to why we'd even use a TE, let's talk about how our TE works that we use over at Lit. We run the Lit node on AMD boxes using AMD's SEV SMP. The Lit node runs within an encrypted VM inside of that so that not us, not any of the node operators can even see what's going on in there. Even if you got into the machine, you can't read the memory. Memory's encrypted. And we can't actually read the disk either because the disks are encrypted and are only decrypted by the VM themselves on startup. So here's a quick diagram that's, if you've read the SEV-SMP white paper, it's sort of it would look quite similar to the diagram you've seen in there. But we have the VM itself has a public and private key. It sends a hash of its public key to the secure processor within the AMD CPU and gets back its attestation report. And in our case, the node would request this attestation report, send it along to the peer nodes within the network, who then, once verifying that using AMD's public keys, which are open and on the internet, can then accept that the node is running securely, accept into the network and start sending data back and forward. That's sort of the approach that we use for verifying that a node is running in a secure environment first. Now that we sort of know how we use a TE, I'm happy to answer any more questions anybody might have, but there's not too much to it. Why would we even want to? Well, why does it matter? There are other ways to keep stuff secure, but security is the main reason why. And nobody can access your data. And as I said, this isn't just down to the TE because anything running in a TE is still susceptible to side channel attacks where you can monitor sort of what's sort of the memory usage, what sort of stuff's going on within there. But the threshold on top of that means that you'd have to compromise over 2/3 of the network and be able to figure everything out there. We also use proactive secret sharing. So even if you compromise part of the network in one epoch, by the next epoch, it would be useless to you if there's been a change of nodes or even just if you didn't manage to keep your attack in place. So you have to both compromise over 2/3 of the network and do it within one epoch for any attack to be useful. So let's have a look at how we actually use this in practice with sort of our three main product offerings or use cases for Lit at the lowest level. The first is encryption and decryption. So let's imagine we have two parties who the first party wants to encrypt a message and send it to, so Alice wants to encrypt her message and send it to Bob using the lit network. The first thing Alice is going to have to do in this case is sort of decide on her access control. So how is Bob going to be able to prove he should be able to access it? That could be maybe Bob has to prove ownership of an Ethereum address in sort of a basic example, but it could be anything to having to prove you have a certain amount of tokens and you control this GitHub account. So as long as it can be verified by all of the nodes, it can become an access control rule. Once she's done that, the ciphertext can be created from there, which the ciphertext is sort of both based on what your access control rule is and what you're actually trying to send. So let's say hello world. And then she's going to send both this ciphertext and the rules over to Bob. Oh, now that Bob has these rules, he can send the rules themselves as well as any proof he has. So if we'll just use the simple example of, do you control this Ethereum address? He could send that and a signature to the nodes. Once a threshold of these nodes reply with a signature, those signatures can then be used to recover or decrypt the ciphertext back into its plain text. So the SDK handles most of the abstraction here about sending to nodes and picking a threshold. But the general idea is that as long as over 2/3 decide that it is true, then you can use a subset of your responses to recover that plain text. The other option from there is signing, which is we have a concept of a PKP or a programmable key pair, which is created itself with a set of rules and stored on the blockchain. And anybody who can prove access to this key using the rules the same way as in encryption and decryption can then request the nodes create a signature for that key. So in our example here, we're going to imagine Alice is going to create the PKP herself. But in another example, I could create it for Alice and create the rules that Alice just has to prove ownership of an email or a phone number and then has access to the key herself. So Alice wants to send a transaction with a PKP that's managed by the lit network. Alice requests the PKP with rules from the nodes. The nodes then provide the address of the PKP. And she can then create her transaction. Maybe that's in a sim. We'll imagine the PKP has some funds put into it before she creates her transaction. And she now wants to send maybe 0.1 ETH. Maybe she's feeling generous to me. It's my lucky day. So she'll create this transaction. And then what she'll do with it is she'll send it to the nodes to sign, along with, again, some form of proof that she meets this set of rules, this criteria. And provided that, again, 2/3 of the nodes agree, the signature can be returned, and then Alice can submit this transaction. So that's sort of the encryption and the signing side of it. The final thing we have is lit actions, which is, imagine you have all this code now, you've decided you want to use lit, you have a grand idea, but at the moment, you're thinking you're going to have some kind of backend to manage this data. Instead, you can run your own product code within RTE and sort of call the lit methods yourself and call them from a front end. So you then could deploy an entirely decentralized application where your front end is hosted on IPFS or Arweave. The sort of keys are managed by lit or managed sort of by the lit network. And then your sort of backend code, your actions are also managed by or handled by the lit actions service. And they're immutable. So once you publish a lit action, it is then that version for as long as it is until you update it. And then by updating it, you get a sort of new point to call. So I've run through that a little bit quickly, but I'm happy to go through and answer sort of any questions anybody might have revisit any bits, and maybe I could get up like I guess a whiteboard and go through anything like that as well if people have further questions or maybe more diagrams are needed.
All right, thanks a lot. And yeah, I'm sure we'll have a lot of questions. I have like 50. But Leo is front running us all and asking in the chat if you can describe the hardware that the nodes are running on.
For sure. Let me get up instead of this for a bit. I'll switch it to. I'll switch which screen I'm sharing, and then we can get some. Let's share this, and we can go through anything else on here to sort of make it a bit easier. So our nodes currently run AMD EPYC chips. We have a mix of Milan and Genoa in use by a few of our different node operators, and most of them are in the US at the moment. The node operators, there's a list of them in the lit docs, which I'll get up now. I believe there's about 10. However, I don't remember them all off the top of my head. Yeah, so we mainly have sort of the ones that are on here on the documentation, and I can check internally to make sure it's been updated recently, but I believe this is the up-to-date list of who's running nodes for us. And at the moment, we run a few as well for the test nets and with the production networks.
All right, maybe a follow-up. Do you have any performance requirements for the nodes? Are those small boxes? Are those big boxes? Do they have like 2 terabytes of RAM?
The nodes themselves have a mix of RAM in the sort of, I believe it's 32 to 64 gig range, and they have between 16 and 32 cores. But the only requirement that I know of is that you have SEV-SMP support. So it would have to be an AMD EPYC chip at the moment for a node to be run.
All right. So yeah, Andrew is asking in the chat, what are some fab examples? I don't know if I know what that means, Andrew. Maybe you can clarify. Yeah, and there's actually a second question that I also want to ask. Is it important whether you know what's running inside those lead action programs, right? Yeah, maybe can you tell us about that?
Is it important for us to know what's running in the programs, or?
Yeah, in the lead actions.
We have no idea what runs in them. They're running their own Deno runtimes. So let's do this. So we sort of have let's say this is an individual node. It's obviously more nuanced than this, but imagine there's a node, a request comes in to run a lit action, and then it's run within its own runtime inside the TE. There are rules about, I believe, what can and can't be run inside it just based on what the runtime has. And I can find, I'm sure it's in the documentation about that, but I personally haven't used the actions too much myself. But there are plenty of examples on here. But the only requirement I know is that it would run within the Deno runtime, and I don't believe there are certain external dependencies that are supported yet, but I'd have to check.
All right, I have a follow-up question. Sorry about asking a question about the lead actions. So if I understand this correctly, you're saying that side channels are not necessarily a big concern for you because you have threshold encryption, and you would need to break, 2/3 of the nodes within a single epoch, which is, a hard task, especially if the operators, are there's many operators, right? There's like 10 different operators, so that's good. But that doesn't necessarily help with the lead actions, right? Because it's a program that you don't know. So are you thinking about side channels inside the lit actions?
Yeah, my understanding is that a lit action is run across multiple nodes as well. So the same protection of threshold applies there. But of course, we can never entirely mitigate side channels. You could have one malicious actor that is set on running a node and trying to find out what's going on inside it. But at the moment,
Interesting. So is it like MPC inside the lit actions if you're saying that multiple nodes are running it?
that would be my understanding, but I can always check and get back to you and reply here and on the thread we have on the.
Amazing. Oh, so Mike is saying that lit actions run in a separate process
Yeah.
in the T. So, all right. Interesting. So I actually have a related question about the PKP. So,
Sure.
so if I want to generate, can I generate like an Ethereum transaction can I sign it in an Ethereum transaction?
From a PKP?
Yeah.
Yeah.
So does that mean that the signing key is it also MPC, or is the signing key decrypted somewhere in a specific node for signing?
My understanding is that the key would never be decrypted. Mike would know better as sort of a cryptographer on that side, but my understanding is the key is never decrypted per se. It would be MPC.
All right, yeah, because then again, side channels could be a concern if it's MPC. The signing key computes the signature over MPC. Amazing. All right, let's go. So yeah, this I think this does prevent side channels to a good extent. Andrew, do you have any questions on the side channels? I really want to exhaust this topic before we move on.
Yeah, definitely. I wondered if there were, I guess I still don't understand the total range of things that the actions or things using the actions can do. Is there some need to follow like software guidelines to mitigate side channels or limit them, or even just characterize which ones for your application you need to worry about?
So the code that you put in the action runs within the TE, so you still have the same side channel issues that you would just by running code in the TE yourself. So I don't think it's just mitigated because of that, but my understanding would be that if it's run across multiple nodes with MPC, then there wouldn't be that sort of side channel issue. But I think that would come down to specific implementation details and what you're trying to do with lit actions.
All right. I'll shout out one question from Mo, which is Mo was asking if if it is deploying the nodes on specific cloud or also bare metal, and Mike has replied that it's all on bare metal right now, which is of course amazing.
Yeah,
but it would support anyone that can run AMD SCV and SIP.
Yeah, all of the nodes at the moment run on bare metal machines, but as long as it supports SCV-SMP, like Mike said, you could run a node on it.
All right. Mo has some more questions about the lit actions, and people will have to ask questions, also other questions, not about lit actions. So Mo is asking whether the actions allow storing persistent state for later calls, or is it all ephemeral?
Lit actions is not my specialty, but my guess is going to be they can't store anything sort of on the nodes. It's entirely ephemeral. If they wanted to do something like that, they would have to use a blockchain itself and put data onto there.
And by the way, I think that totally makes sense, because if you want not to have issues with side channels, you really want them to be ephemeral, right? Because having state will literally always means that this will have side channels, right? Because you have the output, the state somewhere. Okay, amazing. Okay, let me go through the chat to see if there's more questions already posted. Okay, so Leo is asking whether you can tell us something about your transition from your test token to an ERC20. And yeah, and also asking some follow-up questions. Is the token a kind of gas token? And if so, how do you quantify the consumption of the token and reward the nodes for running those operations?
For sure. At the moment, we just use the test ERC20 token, and I don't know, I can't give you a date about when it would become a sort of real token or anything in that. But the idea behind it being a gas token is correct. And the quantification, I believe, is on how much work the node actually has to do, and based on how busy the nodes are as well. So considering you need a threshold when you're looking for that, we imagine it's 10 nodes, you need 2/3, so that's 6 nodes. Instead of just picking nodes, you would pick the 6 cheapest, and then as those nodes get busier, they get more expensive. So then the network load balances itself.
Right. I guess this also answers a question from Meffi, whether there's performance limitations to how many nodes can participate in the MPC. So for 10 nodes, you'd pick the 6 cheapest. So I guess that you can't pick a lower number, right? Because you need to satisfy the threshold, of course.
Yeah.
So are there any performance limitations? How do you envision the set of the nodes getting bigger, like more than 10, like let's say 100 in the far future?
I believe there would be performance limitations on that. Mike probably knows better than me what they are and at what point it starts to affect us. But we are trying to keep the node, even on an individual basis, as performant as possible from looking at whether that's changing OS or upgrading OS and that sort of stuff. And then we can think about the end at some point. But Mike said we're looking to sort of grow it to 30 soon, rather than the 10 nodes, which will mean that a threshold would be 20 rather than 6 that you would need to meet the threshold.
All right. So there's no more questions asked actively in the chat. As I'm saying that. Okay. So I have some questions that I'll get out there. So how does mainnet look like to you? So you're right now still on the testnet, right? And I'm not asking about like a time, a place in time, like a point in time, but rather what kind of features, what kind of guarantees do you want to build before you want to call this protocol like a mainnet?
I think we're progressing quite well towards a mainnet. I know you said you don't want timelines. I personally don't know a timeline for that, but I believe there are a few more things about a performance that we want to get in before we get there. We want to make sure, as Mike said, we can perform well with the 30 nodes that we'd like. And as you said about scaling to 100 nodes, we want to make sure that before we get anywhere near that, we can have the performance there that we need. We need to keep testing, and then I imagine that more features will come as we go through that, whether it's a case of removing stuff for simplicity and then adding other stuff for features customers are asking for.
All right, amazing. I have like limitless supply of questions. So can I recover? How do you see disaster recovery? What kind of disasters do you see happening in the network? And do you have a way to prevent a disaster or like mitigate or recover from a disaster?
I believe we have a way to recover the shares that isn't just us. I believe there's a set of recovery parties that all have to complete a set action sort of around the same time and recover together. And that will be our disaster recovery. A node can join and leave the network as long as there's enough for the 2/3, is my understanding there. So the only sort of disaster could be all of the nodes get wiped out or all of the nodes lose their shares. And I believe we do have a recovery method in place if this does happen.
All right. So I don't want to monopolize the time. So Andrew is asking, what are your thoughts on how to do remote attestations, right? Do users or auditors pay close attention to the remote attestation process and reproduce the build for for the local measurements to verify the attestation?
As in attesting that the T running is the correct code?
Yeah, that is the correct code, and maybe if it ties into audits or something like that, that it matches the end-to-end guarantee that it does what users expect.
For sure. A project that I've actually been working on it internally and is hopefully something soon is a system for you being able to verify builds, us being able to publish our build environment, and then being able to let people take the code, build the same binary, verify that the hash of the binary they made is the same as the hash of the binary that is running within the machine or should be running within the machine. And at that point, you have a way to attest that the code running in the TE is the same as this set of code you have there for the node. And then obviously when you were talking about audits and auditors, you could then compare commit hashes and that stuff with known commit hashes that have audits in the future.
All right, amazing. And while we're on the topic of remote attestations and the hashes of the binaries, I imagine that the code that the nodes that the operators run isn't static, right? You upgrade the code, right? You make changes.
Of course.
How does it look like?
We have a fair amount of sort of internal tooling at the moment for managing the machines and updating them, and the sort of flow is that it gets published. The long-term goal, my understanding, is that it wouldn't just be us as a company that could publish an update. It would have to be a decision by a wider body, decentralized, preferably, that decides and publishes the updates. And I understand that contract updates go to the chain, and that any sort of software updates is a case of individual operators running a command on their box, which would update the software being run. And with the new attestation stuff we're working on, verify that the new code they're going to run is what should be there.
Right. To follow up on this, so this of course is a huge factor, right? And we know that upgrades are very difficult to execute correctly, and codes and bugs and issues happen. So I have a question. So how do you see this working better, right? So this is not something that's only the case for Lead, but I do believe that basically all of the T products are suffering greatly from the upgrades process. And we at Flashwares have also thought a lot about upgrades, and we think this is one of the main issues. What's the ideal solution? In the ideal world, you have unlimited engineering power and research power to solve this problem. How does the solution look like to you?
And me personally, I think some kind of hot reloading solution would be nice, where you can switch out what's running on the TE just by giving it another sort of signed binary. Whether that's ever even feasible is an entirely different question. But I think that would be my personal preference. I think sort of short to medium term with more feasible stuff, it's a case of making sure that everything is validated either manually or by deployment scripts before it's ever even sort of published or run on the node, or in this case on the bare metal box. So the node is only ever running if you have a verified sort of signature or sort of key from that box or from the binary even.
So let's go for like a what should you call it, like a malicious actor signing the code. So what can a user do to prevent their secrets being accessed after a vulnerability in an upgrade? So let's say that there's an upgrade. We know that a malicious actor has taken control over the software signing key, can the user do anything to prevent their secrets from being accessed on this newer malicious version?
Unless over 2/3 of the nodes have updated to this malicious version, there's the user should remain fine. The only time that will become an issue is if over 2/3 of the network have updated to a malicious version. And at that point, the user can't do too much, is my understanding about this. But the way that updates work is it should be a sort of a smart account wallet with sort of multiple signers involved. So it's not one single key you have to compromise. You'd have to compromise multiple people.
I see. All right. I had an idea pop into my mind. Could you define this as a part of your what you call it, access control? To say, as a user, I only trust this specific version of the nodes. Could you do something like that? I guess you can't really, because the threshold shares are for like a master secret, right? Right, not for any particular user's secret.
The threshold signatures are the signatures given back to you by the node are for your specific decryption, but the whole it could work, but you would then not be able to decrypt between updates. Imagine I've updated my node, you haven't. It wouldn't work there, and I'd have to check whether the sort of PKPs allow those sort of rules. But if you can, it could be a good way if you wanted to. Although it would potentially rule out ever being able to access that key should the network upgrade too far past it.
I see. Yeah, I'm asking because this is one of the problems that we see as, like a malicious version of the code is something that can do almost arbitrary amounts of damage, right? So it could be interesting to think about ways to give the user some kind of way to prevent it if they really are scared about this vector.
Even with that, though, a malicious actor could change the logic for accepting or declining rules. So I think you get back to the same point, because their malicious node code could just sign whether or not the rules are passed.
Yeah, I think that's only the case if you get I guess that's only the case if all of the different versions of the nodes software have share the same, like have the threshold over the same secret share, right? But if you every version change add a new secret, right, then that actually wouldn't be a problem, because the new versions wouldn't actually get the secret share.
Yeah. So as long as, but then you get the solution's the same as just trusting that at least the threshold of the network is still safe.
I see. All right, Andrew, do you have any follow-up questions? I know that you think about this a lot too.
No, I followed that. That made sense.
All right. So I'm always asking whether you are using a fully scaled VM, for example, Ubuntu, or a customized VM with your code. So yeah, I'm curious. So Mike is saying that you're using the latter, which is a customized VM. Yeah, what are you basing this on? This has been something that has, really pained us because we are using Yocto right now, and it's not the most pleasant. Yeah, how have you solved this?
We have a custom Debian-based VM that runs just the node code, and it's built by some of our internal tooling. You have it on one box. Sort of you have an AMD SEV box to produce this image. You produce it, and then you release it from that box, and then as part of sort of the deploying side, you would be able to, as Mike's saying in the chat, you'd be able to actually verify all of this with the new verifiable build stuff we're planning to release. But the idea is that the code is in the VM. Everything's built in a TE anyway, so we can't tamper with it when it's built. And then when you get the image or the sort of the release, before running it, you can now check all the code, verify it. And then once it's run for that first time, nobody can ever get back in it again. So it's then just running a lightweight VM which only runs our code.
How do you actually enforce? How do you enforce this guarantee that nobody can ever go back to the build VM?
The disk is encrypted on first startup, and then is only ever accessed from within a TE itself, and the key is stored within the TE as well. So once that first startup's been done, even the disk image is useless to you, and AMD SCV SMP has all memory is actually encrypted as well, so you couldn't pull it out of memory. The only attack that would be still viable would maybe be side channel, but I still don't think that would actually get you inside.
It could get you the disk encryption key, right? But I think it's very difficult to do if you can't make repeated use of the key, and I don't think you can do that. But can you snapshot so let's say that I'm running a bare metal, right? I can actually snapshot your build. I can snapshot the build VM, right?
The
Like
build VM?
Yeah.
So builds are done
Yeah.
within a TE themselves. And with AMD's SCV SMP, the memory is also encrypted there, and it's running again inside of a VM with an encrypted disk. So a snapshot from the bare metal wouldn't help there. And I know Mo just asked if there's a dedicated TE builder VM that builds the images. And currently it's done by hand, as in a member of the team SSHs into one of our boxes, uses a custom CLI we built, which builds this sort of image along with the metadata about it. And then it can be published to the chain with its release information, provided that they can prove they control this sort of account that's in charge of that, which is monitored by the smart contracts decide that.
Interesting. Can I ask a question here?
Sure.
So if I understood this correctly, if I am now as an outsider would like to rebuild to ensure basically reproducibility on my side, like basically I want to initiate the trust by doing everything by my own as an outsider, would that be feasible? Like what's here the blockers for reproducibility in your opinion?
Currently, no, it's not possible. With the verifiable builds feature we plan to release soon, yes, that would become possible for you. You could get the image, get the code out of it, and use a published Docker image or a published build environment to then put the code back in there, rebuild the entire binary in the same way we have, and then compare directly the two hashes to see whether the binary that's inside of our TE image is identical to the binary you would get with the same code.
Amazing.
Cool.
Yeah, and I'm sure we are all very curious to see this tool, because this is something that we have. We are not happy. We do have the reproducibility of VMs, but it's very difficult to set up and takes a lot of effort to change anything, like to modify the image. Right, and Leo is suggesting that we now let you ask some questions if you're curious about anything about Flashbots that we are building as it relates to what you have here.
I guess my main question is, how do you guys use TEs differently to us? I know we're using it to prevent sort of the typical theft of data, but I believe you guys use it in a slightly different way.
Yeah, I think so, and they are very complementary too. So we are not doing any MPC on top of the T's, so we are subject to side channels, and this is kind of our nightmare, right? Like trying to battle the side channels, which are very easy to miss in your code, and so this is like one big difference, and that's because of a difference in the kind of problems that we are solving, right? Of course, for your use case for secrets and keys, MPC is ideal and should be performant enough at this point. So I think the main difference comes from the fact that we are trying to run almost arbitrary code inside the TE, so that multiple distrusting parties can agree on something, right, with a very high performance. So this MPC doesn't solve the problems because it's just not performant enough. It's not like, oh, it's just slower. It's actually too slow to fit the requirements. So it has to be kind of native and inside a single T. And because it's not MPC, it can actually be arbitrary at that point. But yeah, side channels everywhere. So I think that's where the biggest difference is, just because we are running arbitrary programs. Yeah, so this comes with a different set of aches, let's say.
Yeah.
Persistent state too.
Yeah, persistent state.
Yeah. Have you guys managed to do anything to mitigate the side channel attacks that your sort of code's susceptible to, or not yet?
So we actually have ORAM implemented in 2 services at this point, which is kind of interesting. So we have not prevented every side channel, and I don't think we'll ever do that. What we'll try to do is document all of the side channels, right, very well, and be very explicit about where is danger of side channels. But we know how to use, let's say, ORAM to mitigate at least some of them. So we actually have like an unpublished version of, and like the reason I can say this is because we don't have any products live on like production that are using this. But yeah, we have ORAM in like 2 small POCs, not so small, that you can use to hide access to some of the persistent data at least. Yeah, otherwise, no, we have not done a lot of effort other than researching ORAM in depth and also at scale, like putting a lot of data into ORAM. There's a team from LNG working on this, right, of ORAM, and they're doing some amazing stuff. They're putting like hundreds of gigabytes of data into their ORAM key value store, and it's very performant. So this is something that we haven't solved yet, and I don't think we'll solve all of it forever. But there's very concrete things you can do to prevent at least some cases of the side channels. I don't know if that answers, but
yeah,
that's it.
Yeah, thank you very much.
All right, Adam and Mike, do you have any questions to us? Right, I'll let Adam and Mike think about it. They're all good. Okay, so we're going to slowly wind down. I think let's ask some more some last questions. So just like a very open-ended question. What are you most proud of, athlete? Like, which part of this are you the most excited about?
I think for me personally, it's verifiable builds, because that was my first project when I started, and it's doing a lot of stuff for people wanting to do stuff. As a whole project, what I'm most excited about is probably the programmable keys, and the fact that you could have a key, and instead of having to look after a private key, you just have to meet some arbitrary set of rules that can be decided by the person who makes the key.
Yeah, powerful. All right, I think we are done. Are there any other questions from the audience? Fred, do we have anyone asking questions on YouTube?
Hey, super interesting stuff. No, we do not.
All right. In that case, thanks a lot for coming on. And yeah, this was really interesting. I hope we all learned a thing or two from this. Yeah, I'm sure we'll keep in touch.
Yeah, thank you so much for hosting us. And if anybody has questions either from your team or on YouTube, feel free to put them on the blog post I saw you guys had on the forum, and I'll create an account and answer them as soon as I can.
This was a great discussion. Thanks for coming by.
Awesome. Yeah, thank you so much.